Okay.
That used to be me helping, not too old now.
Okay, kernel convolution. What this is basically you have this image. It's represented by numbers, and you have a little template for like a little local region of a sort of thing that you're looking for in the image. And what you can do is you can take a part of the image, and you can match this template to the image. And you can cross-correlate them and just basically see how well they match with each other. When you do that, if they match really well, like here, red on red, blue on blue, they'll return a large, high number. Versus here, they're kind of perfectly unmatched. We have red on blue, blue on red, and that'll return a really low, negative number. And if they're sort of matched in between, you return an in-between number. What you want to do is you want to take this kernel and you want to apply this to all the different regions of the image. And when you do that, Colin, it's going to be...
Can you lock the meeting?
Sorry, Chris, I'm just going to be calling like the entirety
The
of
host. No, make them host, not co-host.
Yeah.
Oh,
That's
sorry.
So you drop
Okay, sorry. Gonna
Zoom. It's, even with years of Zoom, it always is this way.
Yeah.
I can do a little
Never
dance.
Oh, he says so. No, never mind.
Make them host.
Yeah,
Okay.
Is it sharing? It's not sharing.
Oh my gosh.
It's all right. It's all right. We're not counting this time against you. The audience will give us.
Oh, hosts. Enable screen share.
I didn't see that one coming.
He's muted. He's giving his own talk.
Chris, a co-host.
Okay, go. I share screen as
Okay.
well.
All right.
We're back.
We know what we're
good.
doing.
It's
Okay,
only
we're good.
it's been less than a minute.
Okay. So
Take your
we can
time.
do this. We can see where this kernel is in the image. Another thing that we have to reconcile is that an image actually can have like a lot of different channels. It's actually composed of maybe a lot of different images with different features. For example, a color image has 3 channels that are composed spatially like this. And we could have a different kernel that we could pass over each of them. And we can then combine channels by taking these activation maps they output and adding them together like this. And that would be like a kernel convolution over multiple channels. And we can have, different channels that detect different things, or different filters that detect different things, like maybe this striation this way versus this way, and we would get a different activation map, and we could detect a lot of different things in the image. One last piece of a neural network, and then you have all the pieces that basically do the whole thing, is let's say we want to do something like, I have this, dark within light detector in this orientation. What if I wanted a light within dark? And what if I wanted a feature that detected both light within dark and dark within light? Could I do that with this? There's actually a problem is if you just have these ingredients, something like this is impossible. For example, if I tried to add these 2 maps together, these are just directly opposite each other. So everything would cancel out and it wouldn't detect anything. So one last trick, one last ingredient that'll allow the neural network to do basically anything is if we first zero out the negatives, called the ReLU activation function, and then I can add these together, and I have an invariant dark or light edge detector in this orientation. Okay, and then a neural network is going to compose these operations in this big hierarchy, and eventually, maybe you can get something like this. Feature detectors that detect things like the people in the image, or the dog, or the faces, the background. These are actually real feature detectors that emerge in one of these networks. The big question is going to become, I have a clicker. How do we figure out what these kernels are? And this is what training neural networks is all about. Basically, you'll have some objective. You'll start with random kernels because you don't know what they're supposed to be. And you'll compute some output target that you want. And they'll have a distance between what the network outputted with these random weights and what you wanted it to output, in this case like a label for bullfrog. And the last thing that we have in these frameworks is we can compute what they call like a local gradient, which is basically just how do I have to change these numbers around locally, perturb them? how will it affect this distance thing? And we want this distance to go down. So then we can locally just adjust these to make this distance go down, and you'll get a network ultimately to learn the correct kernels such that it will, in this case, label the frog as a bullfrog and do whatever you want. Okay, the last thing that we want to know about is this thing called feature visualization, because it'll just come up a lot. You can calculate other gradients. So for example, I can calculate if I want this activation of this feature to go up, how do I have to update the pixels of this noise image to make this little neuron fire here? And it will synthesize an image for you. If you do this for deeper neurons in the network, you can get, richer and richer kind of semantic picture labels for what these different neurons are looking for. Okay, so that's all the background. Let's go into the first chapter here, circuit pruning. So here was a diagram that was very popular that makes some of the functions of these networks seem like they could be something very simple. And basically what you do is you take these feature visualizations for different neurons in the network, and you just connect them by these kernel weights that map between these different neurons. And you can kind of see like a mechanistic motif for maybe how you construct something complex like a car detector. This would be like put a window at the top, but not the bottom, put a wheel at the bottom, but not the top. If you combine all these things, if they're in the right arrangement, this thing will now fire for a car. This is really great. We'd really love for the networks to be simple like this. But one question I had when I saw this is, this is really embedded in this really large network. Is there really this simple structure embedded in this really complicated thing? And how can we justify that? So, first question is, well, how do you pick these are the relevant connections for understanding this car detector? What about hierarchy? Like, okay, now I understand I need to know about wheels and windows if I want to build a car, but how do I build a window and how do I build a wheel? What are the effects of just ignoring everything else? Can we really do this? Or are you going to end up with something that's not at all the thing that you started with? So you've simplified, but you've oversimplified. And now nothing works anymore. Okay, so the way that we're going to do this is our goal. We want the thing that we extract from the model, this simple little algorithm for the car detector, to approximate the full model feature. We want to do so as sparsely as possible. So if we knock out things from here, this is a better solution because it's easier for us to understand. And we want to do this without actually changing the weights. We want the circuit to exist in the model as is. Okay, but which of these connections do you choose? Which circuit is the right circuit? Just for purposes of doing things efficiently computationally, we took a very simple approach, which is basically just to come up with a scoring criteria for these different connections and say, let's leave in things that score very highly and slowly remove the things that have a really low score and see how sparse we can get things before this thing starts to collapse. This is intuitively a simple scoring function that ended up working well, but we checked a bunch. You can basically think of it as an image goes in, this thing fires. This is important if it activates when the image goes in, that's this term, and it has a gradient from this thing that you care about, which basically, if this gradient was small, it would say, you could have changed this and it wouldn't matter. The gradient is 0, it's flat. It's insensitive to changes in this. So there's more formal ways of saying why this is a good metric, but that's intuitively why you might use something like this. Okay, we tested a bunch of different metrics. You can kind of increase sparsity and see how, you can see on this y-axis here, this is a metric for how well you have preserved the feature that you're trying to preserve. It's basically just a correlation. And if the feature is preserved, this will be high, all the data will lie in a line. It would be easy to reconstruct the original feature. And this was the metric I talked about here, the orange line. This is if you did something very naive. And you can see you can do better than doing the naive thing. And sometimes you can get pretty sparse circuits. One thing we noticed that was kind of interesting is that if you do this across different features, you'll have huge variance on how sparse those different features actually are. So this thing you can get super sparse. You can almost knock out all of the network and the feature behaves the same versus, other features start to collapse much earlier. Now, given that we can do this, we can actually just look at circuit diagrams for the very sparse features like this one here. So this is literally here was the original feature visualization for a neuron in the network. And you can knock out almost everything such that you're just left with a diagram like this, and here's like a new feature visualization of what it's looking at, and it activates it behaves almost the same as the full model neuron, and it's much simpler. It's basically just an identity mapping of this guy, goes to here, and then this says, put this in the right, and you end up with something like this. Another thing we checked was, can you get things even sparser by doing like, instead of kind of saying, what's the circuit for this whole feature, can you do it image-wise? So can you say, this feature here, it actually computes these images with this circuit and these images with a different circuit. A way to think about that might be like, let's say the chair detector, that might be two functions, like a front chair detector and a back chair detector. Or alternatively, it could be just like, there's just one thing that's shared between these two. And this is what the neuron is looking for. You could imagine something similar for like faces and balls. It likes both. It could have separate circuits computing each, or it could just be like a general blobby orange detector thing. You can kind of formalize which situation you're in by seeing, given one set of images versus another, if the circuits are overlapping or not when you do this extraction process. So we did this as one example for polysemantic features, which seem to respond to multiple different kinds of things, like it likes these curves, but it also like these metal lines. You'd kind of think that this would be the case of like disjunction. There's actually two circuits here, and they use different weights, and they're getting added together. But maybe we're in this regime, and just something really crazy is going on. It perceives the world very differently than we do. Anyway, you do this extraction process. You can either extract circuits with respect to the terriers or freaking metal lines, and you can see how sparse do you get before the way it responds to these images starts to drop off. And we get similar motifs to what we had before. Now, the interesting thing is you can extract circuits with respect to, for example, the dogs, and see how that neuron responds to the metal lines. In this case, it decays much quicker, basically saying the circuit that computes dogs cannot compute the metal lines. Once you start to extract that, it no longer responds highly to the metal lines. And you can check explicitly at like a certain level of sparsity how much those circuits overlap with each other. You can do it as a function of layering. So they don't overlap very well at all. You can recompute the feature visualizations. You can see they're looking for actually different things. So you can split up the network this way. I developed this tool to try to do this like at scale live with a million different things, and you can pick the feature and you can pick the images that go in, and you can try to lay out the whole model. And I was working on this for a while, but there was something I found that it's just like very overwhelming. It's a lot of information. I kind of had the opposite instinct of, well, can I instead use these circuits to represent the information as simply as possible and get rid of everything? So the opposite instinct was to do something like this. I saw that when you do these simple circuits, the feature visualizations become very simple. They're kind of like a simple prototype of what that feature is really about, the red dot, and then maybe this stuff is like less important details that you add on later. So the opposite of our huge GUI where we can explore everything interactively is just to take these circuits and get everything in between and visualize this as a video. Kind of how do you like paint the feature from its simplest constituent to something complicated. You do that, you can get these nice videos like this, where maybe at the end you have something that was like a arch detector, and you're kind of seeing how the model wants to paint that by first doing, the simple contours like this, and then what's the details, so what are the things that are getting painted on at the end. Okay, next part, feature accentuation. Everybody would call it Srijini.
Sorry.
Why aren't you here? So one thing you'll notice when using these neural networks, you might be in a situation where you have a bunch of different, these are logics at the end, and there are things that you know, this is supposed to be a neuron representing an iguana, representing a frog, representing a chameleon and a newt, and they all kind of like this image. Okay, so usually when people are in this kind of situation, when you want to know, well, why does the chameleon like this image? They'll use this technique called like attribution maps. And this is a huge part of the explainability literature. One thing that can be problematic though, is it's basically just telling you what are the important pixels for why the chameleon logic liked this particular image. And you'll find yourself in circumstances where maybe across a lot of different neurons, they all like the eye. Okay, so you can either say, okay, well, they all like the eye, but like, does the chameleon like the eye for a different reason than the frog likes the eye? Is it actually something different, and I can't really visualize what's going on with just the heat map? Okay, the alternative is you do something like feature visualization from noise, as we've been doing, but this can be tricky too, right? Because you say, okay, well, the African chameleon likes this sort of image, but what does this sort of image have to do with this image? I want to know why it likes this image. So I wanted to kind of come up with something that's in between these two extremes. We came up with this technique, feature accentuation, which what it's going to do is it's going to augment the iguana image to give you, why does the newt like it? Well, because it's approximately like this newt. And why does the frog like it? Well, it's because it's approximately like this frog. How do you get visualizations to work and appear nice in this way? There's kind of a problem. If you just try to do a feature visualization, if you try to perturb the image like we did to make, one of these neurons fire, you can easily find yourself in one of two scenarios. One, you can change the image. This is a panda image, and we changed it. This is like a famous example. And now the model thinks it's a gibbon. The monkey neuron says, now it's a monkey. But we don't perceive any change in the image. So you can kind of change too little, and you don't really get any more information than you started with. On the other extreme, this is another kind of famous example, you can change the image too much, and you can say, make this a dog, and it just goes, okay, and it just paints over the whole thing and does whatever it wants. So how do you strike the balance between these two things and constrain your accentuation to the original image you care about without having it, change something perceptibly, but not go off the rails and do something like this? So there's a bunch of tricks basically you need to do to make this work. I'll just talk about one trick that we found that was really useful. One thing you can do is you can say, okay, change the image, change the pixels to make this neuron that I care about fire, but do so such that in another layer of the model, under another kind of parameterization of the image doesn't change. Now, normally when people do this sort of thing, they would say, what's that other parameterization of the model? Make it so that, for example, make the monarch butterfly fire, but make the pixels not change that much. The pixels themselves has to stay close to the original pixels. When you do this, you might get something like this or something like this. Now we found if you did this in the latent space instead, you get much more concentrated changes, and you don't get kind of these aberrations all over the whole image. I think this is kind of nice because there's actually a very intuitive explanation for why something like this works. It's just that in pixel space, the absolute values of pixels aren't a really good feature to be preserving. So for example, this image here, can you guys see the stripes on this projector? Mm-hmm. In pixel space, this is halfway between this image and this image. Because these are slightly different shades, and I just took half from this image and half from this image and striped them. So it's halfway between. But you probably see something more like this. This is over here, and these two things are exactly the same. Pixels see them like this. In the latent space of the model, the latent space will perceive them in the way that you do. These are the same, this is different. Basically, we're boosting contrast, and then we don't get these subtle aberrations over the entire image. Okay, what is this good for? One application we thought that was interesting was something, how am I doing on?
It's 11:30, so.
10 minutes?
Yeah,
That's
you got
perfect.
it, we had some technical difficulties.
We had some technical difficulties. Okay, so one application that we thought was pretty nice with this is sometimes models will misclassify things. For example, this is a barber shop, and the model says, what do you think this is? And the neuron at the end corresponding to moving van fires the most. It's like, this is a moving van. Do you guys see that? Is that obvious? Not maybe obvious. Maybe some people don't already see it. If you can't see it, this is what we thought feature accentuation, one of the things was good for. You say, well, make it a moving van. Why is it a moving van? And the model will kind of tell you what it's hallucinating. Adds the wheel here, here's the big body of the van. It kind of accentuates the window of the van here. That's a moving van. And honestly, I think that's why the model thought it was a moving van. You couldn't see it before, but now you go, oh, I get it. It saw that in the image. You can imagine with a heat map, this might not be obvious. You can do this for a lot of different examples. So for example, this is an ox, it thought it was a Rottweiler. That's because the knees are like Rottweiler faces. It just helps you. Or this is like scales, it thought it was a seal. That rock's a seal. lowest part of the scale is the seal. A fountain. This one actually, I thought it was a dog too, but it just helps you a little bit. There's the dog. It's not a fountain. It's a person playing with their liquids. Okay. You can do this in the latent space as well. These are like output neurons with real semantic meaning, but you can do this with kind of abstractions within the model. So like this guy, or let's do this one. This pattern here with a feature visualization, what is it like about the coffee? It likes this. This pattern is approximately like this pattern here. Cool. Last chapter, feature inhibition. So what is this all about? Here's just an intuitive example that makes sense to me. Why isn't this a banana? For you, perceptually. I mean, it's kind of like a banana, right?
Yeah.
It's almost exactly a banana, really, if you think about it. But maybe if I didn't make this comparison, it's obviously not a banana, it's a duckbill. Okay, but what's going on? I mean, why do we care about this? Really, this is interesting, right? Because in order to have a good banana detector, these duckbills have to not be bananas. Or else it's just not very useful. You haven't really built a banana detector at all, unless the duckbills aren't bananas. Okay, the problem in the literature is this idea of like what is not a feature is pretty much not explored whatsoever. We, myself included with the sort of techniques we've talked about so far, all of the interpretability literature hinges on this idea of like a maximally exciting image for a feature. So we associate with a feature, we say, what makes this feature go? And then we just look at examples that are prime examples for that feature. But that doesn't tell you why the duckbill is not the banana, right? We need to know why something is not an example of the feature. Okay, so well, maybe you could do the opposite, right? Maybe you could look at maximally inhibiting images. Those images that make the feature most suppressed, most return like a negative activation. Now, sometimes like if you're really early on in the network, you can do something like this, and things are pretty sensible, right? Like here are some examples of things that this neuron really likes. It's an early edge detector, kind of like the one we explored at the beginning. And the thing that it really doesn't like is this. It's kind of like spatially flipped. But you'll notice as you go deeper into the network, this becomes like chaotic. And in maximally inhibiting images no longer really bear any resemblance to their excitatory counterpart. So like, why is the opposite of this Orby shiny ball thing terrier? I don't know, dogs. I don't know. And does it even make sense to say that shiny Orby balls have an opposite, or that ships have like a visual opposite? It's not clear what maximally inhibiting images are supposed to mean for us conceptually. There's also a problem in the model. Is remember we talked about this ReLU thing. What the model's doing is it's saying, here's like our feature direction, here's things that it really likes, and then we say, oh, and here's things that it fires really negatively for, and then the model says, get rid of that, I don't care about that. It throws away all that information anyway. So the model doesn't care about what the maximally inhibiting images are. So this might not be like a very useful framework for thinking about this sort of thing. Okay, so we thought, what about like images that excite and inhibit a feature at the same time? What does that mean? A feature just returns a number when an image goes in. But one thing you can kind of do is you can say, well, like, how is this feature built, right? So for example, like a linear case, I can have some number, and it could take like 4 inputs, and they all have a weight. And those are kind of like the parts that get added together to say why this thing's gonna fire or not. Now, there's 2 ways that something could not fire. It could be in this regime where it's uninterested. Nothing makes it go or not go. But you also would get 0 activation for this, which is kind of more interesting. Something's actually happening. There's some components that are making it go, and then they're going to cancel out, but some other components say don't go, and you get a 0 this way. So we're kind of interested in this case. This is like a case of inhibition actually doing something, preventing something from firing when it would have otherwise. Problem is, this is like a linear case. We're in this nonlinear case, but we've already kind of dealt with this in the circuit pruning stuff. We can approximate the importance. We can kind of get this importance vector. It's kind of like just these terms here, and we use this activation times gradient approximation. It kind of approximates the linear case. So we can kind of increase the dimensionality. So rather than have the feature just return one number, 0, now it's saying, well, it's a 0 because it's 10, 5, minus 5, 10, or is it 0 because it's 0, 0, 0, 0, 0, 0? One thing we're going to do now is we're going to take this vector, and we're going to consider what's the sum of all the positive terms, or what's the sum of all the negative terms, right? So we can have these two different regimes. We're gonna just, as a case study, explore this case of a curve detector. And here's what we're looking at, right? A bunch of images go in. The color is how much the curve detector fires. And here's the sum of the negative terms inhibiting the curve. And here's the sum of the positive terms on the x-axis exciting the curve. And one thing we're gonna do is we're gonna kind of look at different regimes. So like what happens when it has positive terms going in, but not so high negative terms? The curve detector will fire. And what we can do is we can actually do this spatially by looking at individual positions of the image and using these same metrics. And we're going to color it this way. So here's a bunch of images. Here's what makes it go. You see it's picking out the curve. This is something that's exciting it. You can also look at inhibition. That's over here. It's high, but it's not far on the right. It's kind of curves in the opposing orientation, and it doesn't like that, so it doesn't go. But remember, we're interested in these other cases, right? So for example, this is a zero case. Nothing's happening, and it doesn't pick out anything. It'll actually pick out like dead regions of the image. There's nothing there, there's nothing making it go, there's nothing making it not go. So this is a zero activation, but you could also have a zero activation by being up here. There's stuff that can go and not go. Then you can get stuff like this, right? You get like the different versions of curve in the right orientation and curve in the wrong orientation. So really what these things are telling you is, look, here makes it go, the right curve. But here, don't go, it's the wrong curve. What we thought was interesting though is usually you don't find yourself in this clean case. Oftentimes you'll find yourself in a case like this, where you get green. Remember, there's a channel dimension. There's a bunch of really images stacked on top of each other. And so there's something in the same location that's making it go and not go. How do we visualize this? This is kind of the same circumstance we were in with feature accentuation, right? We kind of have the tool to tackle this case. So here's the same cool curve detector. We have this little trick where basically we are exaggerating that part of the vector that makes it go and the part of the vector that makes it doesn't go. You can even do this for noise, but you can decompose a given image that makes it go and not go into the part that inhibits it and the part that excites it. And you can do this for different examples. You can do this for different features. This one I think is kind of cool. This is a feature visualization of what it really likes. This is what it doesn't like. Here's something that makes it go and not go. It goes, it likes it because it's like this, but it doesn't like it because it's like this. Thus, the feature as a whole does not respond to this. It's selected, even though there's a part of it that kind of wants to make it go. Okay, we can also do this in a global framework. So instead of just having these two dimensions, really each of these points is like a vector of positive numbers and negative numbers. And we can just take all these instances where that vector is high, where there's something making it go, something making it not go, or both. And we can project those vectors into a distance-preserving two-dimensional space, and then visualize these new vectors corresponding to averaging all the vectors in a part of this space. So if you did this for your curve detector, you get something like this. Here's all the stuff that makes it go, but then there's all these inhibitory curves surrounding it. Now again, the point of all this is not to say we want it to respond really negatively to this stuff because it throws away the really negative stuff. The point is, this stuff right around where it's right gets inhibited. So that's a thing. How much time do I have? There's one last.
It's 11:40.
Okay, so just very quickly, there's some problems with this sort of thing. Here's just a simple toy model to express the problem. It's called an XOR function. So you can implement XOR, which basically means and or, but not and. So we could have two inputs, and we want this thing to respond when either one is on, but not when both are on. Now the interesting thing about a toy model like this is when you have both on, we have a little and neuron here, and we have an or neuron, which responds to as long as one of them is on. And when they're both on, this is like our maximally tense case. It's kind of like a simple version of the sort of phenomena we're talking about, where this doesn't respond when 1 goes in because this fires and inhibits, even though the or fires and tries to excite it. One thing in the interpretability literatures that is important is basically you can have bottlenecks. So we could do a bunch of these XORs, like here's one, here's other. They do it for different features.